Sanjay sir, how is Prayagraj?
Nice.
Our two members are in spaceship.
So we can proceed, I think so.
So I think Ankit has successfully defended his thesis.
Yes, sir.
Congrats and Ankit for being a doctor now.
Yes,
You are Dr. Ankit.
Yes, thank you, sir. Thank you very much. So shall we start, sir?
Yeah, I guess we
Yeah.
can.
Okay. Good afternoon, everyone. Myself, Ankit Kumar, and I am a president of Northern Council of AIP, and I welcome you to all our weekly lecture series. And today's talk is interference as a gateway to exploit dual nature. And this talk is given by Mr. Kaushal Agheda, who is a assistant professor in Department of Physics in Maharaja Sayajirao University of Baroda, Gujarat. He is also president of Gujarat chapter of AIP, and further he is also a research scholar in material science. Our today's speaker is an intrinsic capacity to convey complicated ideas into a simple and entertaining manner. He wishes to motivate his students to get a better idea and respect for the topic. Further, his material science research focus mainly on the experimental research. Additionally, he is also expert in DFT and molecular dynamics. Socially, he is a member of both Vivekanand Kendra and Vigyan Gujarat. And he is also a prominent contributor to both the organizer. So I now welcome Mr. Kaushal to deliver an interesting lecture to today's participants.
Thank you, Ankit. Hello everyone. Good afternoon. My name is Kaushal Agheda, and I am a faculty member and research scholar in Applied Physics Department, Faculty of Technology and Engineering in the Maharaja Sayajirao University of Baroda. Also, I am a president of Gujarat chapter of AIP. So let's start my talk. So today's topic is interference as a gateway to exploit dual nature. Dual nature. So let's focus on the outline of my today's presentation. So first, we discuss about what is optics. Then after classification optics, overview of wave optics, interference, Young's double slit experiment in terms of wave and particle, and dual nature of electron. So, first of all, we focus what is optics. So, optics is it's deal with study of light and its behavior, and how light interact with various material and device. It is a main focus on the so it is a main focus of the optics. And optics is useful in many fields like physics, engineering, medicine, telecommunication, and photography. Of the application point of view, it is imaging and vision. So in imaging and vision, optics is a fundamental to imaging technology, such as the cameras, microscope, and telescope. It also play a crucial role in human vision, such as eye function as an optical system. Then after laser and photonics, so optics is integral to the development and application of laser, which have various uses ranging from scientific research and industrial manufacturing to medical procedure and telecommunication. Then after fiber optics, हमें पता ही है कि फाइबर ऑप्टिक्स जो है कहाँ कहाँ पे जो हम नेट यूज कर रहे हैं वहाँ पे बहुत जगह पे ये जो है वो बहुत ही एप्लीकेबल है. So which is basically which is use total internal reflection to transmit a light signal are extensively used in telecommunication system. For the high speed data, also a transmission over a long distance, it is used. Spectroscopy. So we already know that it's various kind of spectroscopy like IR spectroscopy, UV visible spectroscopy, and NMR spectroscopy. Basically, it's an interaction between light and matter, and allowing the scientists to analyze some composition, structure, and property of the material. Then after optoelectronics. So basically, optoelectronics is combine optics and electronics, and such as LED, light emitting diode, solar optical sensor, and a display. So there are just a few examples of the broad scope and the significance of the optics in our modern world. The field continue to advance and contribute to various scientific, technological, and practical applications. So let's focus on the classification of the optics. So first is the ray optics, where light consists of ray. Then after wave optics, light is a wave, and ultimately the quantum optics. So it consider that a light is a tiny bundle of energy called as a photon. And let's understand the classification of optics. So first is the ray optics. So in the ray optics, there are three phenomena occurred in this or fall on this category. So reflection, then after refraction, and then dispersion. So basically, reflection, it means that we all know that some light is incident on the mirror and kind of medium, and they reflect back to the same medium. And here we can see that some this is a woman, and woman is doing yoga, and it's reflecting its image, or reflection is occurred. Then after refraction, refraction is that light is coming from the one medium and incident on another medium, and which is denser than first medium. So light is a tilt at some angle, and we will get some this like this phenomena. This is called a refraction. And dispersion, we already know that dispersion is that some light is incident on a prism, and we will get some 7 colors on the other side of this on the screen. Dispersion is a very interesting phenomena. So in the late 1800, scientists noticed that the certain elements emitted distinct spectral lines when heated or excited. This line appeared as a narrow band of a colored light in the emission spectra. However, there were some spectral lines that could not be explained in classical physics. So there is a remarkable connection between a dispersion and the birth of the quantum mechanics. Showcase how a study of optics and light led to revolutionary breakthrough in our understanding of fundamental nature of matter and energy. So at that time, when dispersion is found out, so there are many spectra over here, and we cannot एक्चुअली ये जो स्पेक्ट्रा है वो हम क्लासिकल फिजिक्स से नहीं समझा सकते, और फिर वो धीरे धीरे जो है वो शुरुआत सोचने की, कुछ हाइपोथेसिस आए, कुछ अलग अलग हाइपोथेसिस आए, एंड then after we will get some idea of a quantum mechanics of discreteness and all this. So this is a very important thing, and it's a connection between dispersion and the birth of the quantum mechanics. Let's go ahead. So quantum optics. So quantum optics is the interaction between light and matter at a quantum level. And it's combine some quantum mechanics and classical optics to the study of force behavior of photon and their interaction with atoms, molecule, and other quantum system. So there are some point or some concept are fall on the quantum optics. So first one is that quantized energy level, and basically quantum optics explore how atoms and other quantum systems have a discrete energy level. When light interact with this system, it can cause a transition between these energy levels. So it is basically when absorption occur or emission occur. So there are two level, ground state and higher state, and whatever light incident on the ground state, they absorb, and some transition over there, ground to higher state, and then this is called this is because of quantized energy level. Then after photon counting, so quantum optics enable the detection and manipulation of individual photons. Photon counting is a fundamental technique in quantum optics experiment, allowing the research to study the statistical property of light. Then after quantum superposition, so quantum optics investigate the superposition principle where a quantum system can exist in multiple states simultaneously. Then after entanglement, we know very well this word entanglement. Quantum optics is instrumental in generating and studying quantum mechanics, exhibiting uh, quantum entanglement. Then after photon can become entangled. So there is a very interesting thing when when two photon or more than two photons, they distinct, you अगर डिस्टेंस भी ज्यादा है, तो ये एक का बिहेवियर जो है वो दूसरे के विरुद्ध होगा. एंड ये जो कुछ कॉन्सेप्ट जो है वो क्वांटम ऑप्टिक्स के अंडर आता है. Then after squeeze light, so squeeze light basically investigate that which has a reduced quantum noise in one of its properties such as amplitude or phase. So ये जो है वो कुछ quantum noise को भी reduce करती है. ये मुझे लग रहा है कि ये जो है ये LIGO जो होता है, जो जहाँ इंटरफेरोमीटर है और जहाँ पे ग्रेविटेशनल वेव को डिटेक्ट किया जाता है, तो उस ग्रेविटेशनल वेव्स को डिटेक्ट करने के लिए बहुत हायर जो है वो एक्यूरेसी चाहिए और वहाँ पे नॉइज बिल्कुल नहीं चाहिए और क्वांटम नॉइज भी नहीं चाहिए. देन वी आर यूजिंग दिस स्क्वीज लाइट ओवर दैट. Then after cavity quantum electrodynamics, so it's explore the interaction of atom or other quantum system with confined electromagnetic field in optical cavities. Then after quantum nonlinear optics, so it investigate the nonlinear interaction between light and matter at a single photon level. Then after quantum optomechanics, basically it extend to the field of optomechanics, which study the interaction between light and mechanical oscillator at the quantum level. So let's understand the wave optics. And in the wave optics, there are three phenomena fall on this category. So first is that interference, then after diffraction and polarization. So interference is that when two or more than two waves superpose to each other, and will get amplitude higher, lower, or same, and we will get some interference pattern. So this is a kind of interference. In diffraction, whenever light incident on that some slit, and that light is a deviate to that original path, and we will get some diffraction pattern. But again, here is condition is that, so for the diffraction lambda is lambda, it means that wavelength of the incident wave is greater than or equal to the width of slit. This is the width of slit. Okay, it's a small d. So lambda is greater than or equal to small d. Then diffraction occur. Then polarization. So you can see that unpolarized light, and we are putting here polarizer, and we will get some polarized light. This phenomena is known as a polarization. Basically, there are many vibration in many different direction. But whenever we are putting a polarizer, then they vibrate in particular in one direction, and that is called a polarization. हमने अगर नाम सुना हो तो जब हम गोगल्स लेने जाते हैं तो वो लोग बोलते हैं कि पोलराइज ग्लास वाले आपको लेने हैं, तो वो थोड़े महंगे आते हैं. तो बेसिकली इट्स रिड्यूस द इंटेंसिटी, एंड ये जो हमारे आंख जो है वो कुछ हमें जो है वो सही लगता है. सो दिस इज कॉल्ड polarization. This is basically its effect on polarization. So let us understand what is the interference and It is our main point of view or main topic in this talk. So let's start. Whenever water drop is a fall on the water, okay, fall on the bowl. Yeah, you can see that some water waves are generating, and yeah, you can see that this is a crest and trough. Okay, so upper portion it's called as a crest, and lower portion of this wave you can see that it is called as a trough. But what happened when two drop at a time fall on this bowl, and let's check.
Two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with
यहाँ पे
circular
जो है
wave
वो
fronts. Nothing
एक बॉल
particularly
से
surprising there.
हमने कुछ वेव्स जो है वो
if I
क्रिएट
add a
करना चाहा,
second source
देन
of
आफ्टर
ripples,
देखते हैं कि
then we
दो
start
बॉल अगर
getting
एक साथ
an
करेंगे तो
interesting
क्या
pattern.
होता है, and we will get some pattern, and
This
this is the
pattern is
interference.
created by the ripples from the two sources interacting with each other. Where they meet up, peaks with peaks and troughs with troughs, the amplitude of the wave.
So you can see that there is some blank over here, and in between two blank there are some waves. So this is waves because of that constructive interference, and this gap is because of destructive interference. So basically, interference is phenomena in two waves superposed to form a resultant wave of greater, lower, or same amplitude.
Two sources of ripples.
Yeah. So basically, there are two type of interference: constructive and destructive. So when two waves and in same phase, it means that first crest fall on the second crest, and we will get some higher amplitude. So this is called a constructive interference. They construct, okay, higher amplitude. Then after destructive, so destructive means that first waves crest fall on the another trough, and they cancel each other. They cancel each other, and we get some uh, zero amplitude over here. So let's understand mathematically how its amplitude is double or more in constructive interference, and how it's zero or nothing in amplitude in the destructive interference. So there is a principle of superposition governing interference. So basically, when two or more wave trend act simultaneously at a point in medium, the displacement at any instant is due to a superposition of all the wave trend. So let's suppose that y1 is the displacement of the first wave, and that is a sine omega t. Here a sine function or sinusoidal function is introduced because wave is always in form of a sinusoidal. So that's why here sine is up here. Omega is angular frequency and t is a time, and a is the amplitude of the first wave. Then after our second wave, so displacement of second wave is y2, and a is again amplitude. Sine omega t plus phi, some phase. So let's add together, and we will get some resultant displacement when they superpose to each other. And we will get some resultant displacement when y1 plus y2. Here a sine omega t plus a sine omega t plus delta. So in first case, in our constructive interference, so phase difference between these two waves is zero. It means the phi is equal to zero. Then we are putting here over here is a phi is equal to zero. Then a sine omega t plus a sine omega t, it's a twice a sine omega t. It means that in constructive interference, amplitude is double, and we know that the relation between intensity and amplitude is directly it's not directly proportional, but I is proportional to a square. Okay, so intensity is a 4 time, or you can say that brighter intensity we will get in the constructive interference, and and in the destructive interference, phi is equal to so both wave is exactly opposite to each other, and here phi is equal to 180, or you can say that pi. So let's put here a pi. Okay, whenever we are putting pi over here, so a sine pi plus omega t is converting to minus a sine omega t because of the pi, and we will get so they cancel each other term, a sine omega t minus a sine omega t, and we will get nothing. It means 0. So here amplitude is 0, and amplitude is 0, but obvious the intensity is also 0 or minimum. So here we are mathematically we are proving a concept of the constructive interference and destructive interference, why its amplitude is double and why its amplitude is 0 over here. Yeah, let's focus on the interference to the division of wavefront. So interference is basically there are two methods to get interference. So first one is division of wavefront. For the wavefront, the originating from source of light is divided into two parts which serve as a purpose of coherent source. So this is a coherent source. So it's a very again it's a very important property for getting interference. So source should be coherent. Here here some source is there, and it's slit, so there is some wavefront is here, and we divided in two parts. Okay, wavefront divided in two parts through the diffraction, or by putting the slit A and slit B, and uh, uh, and from the diffraction there's two part of the same wavefront, the two part of the same wavefront travel unequal distance, and then after reunite. Okay, आगे जाके वो लोग फिर से जो है वो मिल रहे हैं. पहले क्या था कि एक वेव फ्रंट था, और उस एक वेव फ्रंट जो है वो दो स्लिट ए और बी की वजह से वो अलग अलग हो गए, और दो छोटे छोटे वेव फ्रंट में वो आगे बढ़े. देन आफ्टर कुछ अनइक्वल डिस्टेंस कवर करने के बाद ये जो है वो एक रियूनाइट यानी फिर से वो मिल गए, और जैसे ही वो एट कुछ एंगल पे मिलते हैं, देन वी विल गेट सम interference pattern. The example of this division of wavefront is Fresnel biprism and Lloyd mirror. Let's focus on the Fresnel biprism. So you can see that in image, the source is over here, and whenever two prisms are joined together, and this whole instrument, or you can see that some two prism are joined, and it's a biprism. So whatever wavefront is coming, so due to its prism's characteristic, they deviate or they separate one wave from the one wavefront from to the two wavefront, and we can easily see that here. And at covering some unequal distance, they reunite again, and we will get some interference pattern, dark bright and all this. So here S1 and S2, they are two virtual source. It is not actual sources over here, but it is a kind of virtual, because this shadow, or you can say that this wavefront is focusing on the S1, and this wavefront is focusing on the S2. So this is a virtual source. We can say that. Yeah, so this is another diagram of the Fresnel biprism. This is a prism, and this is a source, and exactly you can see that is a dotted line and that focus and at the S1 and S2. So this S1 and S2 are the virtual sources, and we will and after they some covering some distance, we will interference pattern. Let's go to the another method to get interference, and it's a division of amplitude. It's a division of amplitude. Basically, it is a very similar method, but amplitude of beam light is divided into two parts by partial refraction and partial reflection methods. So basically, यहाँ से जो है वो light आती है. So this is A, B, C, D. This is a thin film, and whatever light are coming from the in air medium, तो यहाँ से मान लो कि कुछ 100% जो है वो लाइट आ रही है, कुछ यहाँ पे 30% या 40% जो है वो लाइट रिफ्लेक्ट हो रही है, एंड बाकी की जो है वो रिफ्रैक्शन हो रही है, और फिर से ये दूसरी सरफेस से कुछ लाइट निकल जा रही है और कुछ लाइट जो है वो ऊपर आ रही है. और मान लो यहाँ पे कुछ 40% लाइट यहाँ पे आई थी, तो यहाँ पे जो है वो कुछ लॉस हुआ होगा या फिर ट्रांसमिट हुआ होगा, तो यहाँ जो दूसरी लाइट ऊपर आ रही है या फिर रिफ्लेक्शन हो रहा है वो कुछ इससे कम परसेंटेज होगा, 30% and 20% and 10% and 5% and all this. So basically 10% or 30% or 40%, it means that it's a reducing amplitude. It's reducing amplitude, and our aim is to divide amplitude in two portion or many portion, and then they two rays or two reflected rays combine together, and we will get some interference pattern. So let's understand. So its example is that Newton's ring and Michelson interferometer. Again, interferometer is used in the LIGO. We will detect some gravitational wave through this. So let's understand Newton's ring conceptually. So basically, Newton's ring. This is a setup of the Newton's ring. So we are using a sodium lamp. And again we are putting over here a convex lens, because यहाँ से जो भी लाइट आ रही है वो जो है वो पैरेलल नहीं होगी, तो पैरेलल करने के लिए हमने यहाँ पे कुछ कॉन्वेक्स लेंस जो है वो रखा है. अब धीरे धीरे जो है वो लाइट जो वेव्स जो है वो आगे बढ़ेंगे, रेज जो है वो आगे बढ़ेंगे, एंड यहाँ पे हमने ये ग्लास प्लेट रखा है, एंड ये जो ग्लास प्लेट जो है वो कुछ 45 एंगल पे रखा है, क्योंकि यहाँ पे जो है वो इंटरेक्ट होके या फिर यहाँ पे ग्लास प्लेट को सीधा ही नीचे की तरफ 90 डिग्री पे यहाँ पे फोकस हो सके, और फोकस होके रिफ्लेक्ट होकर फिर से जो है वो ऊपर आ सके. एंड यहाँ पे ऊपर जो है वो हमने ट्रैवलिंग माइक्रोस्कोप रखा है. बेसिकली aim of the Newton's ring to find out the wavelength of the light or wavelength of the source, and also wavelength of the light. So here plano-convex lens over here. So plano-convex means that one side is a plane and another side is a convex lens. So it is combined, its plano-convex lens, and this is a plain glass plate. Let's understand the basic or what is happened or mechanism of that Newton's ring. So this is a plano-convex lens and this glass plate. Whatever AB ray is incident, and for this lower surface of the plano-convex lens, there's a reflection is occurred, and BE is rays reflected. Then after BC is coming from this air film. This is a air film between this plano-convex lens and glass plate, and again from the upper surface of the glass plate they reflect back, and we are getting another reflected rays, that is a DF, and this is for the one ray. So there are many rays over here, incident over here, and whatever reflected rays we are getting, they combine each other or superpose to each other, and we are getting some interference pattern. So the concept is that in interference pattern, यहाँ पे इंटरफेरेंस पैटर्न में ऐसा हमें लग रहा है कि जैसे जैसे रिंग्स, नंबर ऑफ रिंग्स जैसे जैसे बढ़ती है, वैसे वैसे वो लाइट यानी कि वो जो है उसकी इंटेंसिटी कम होती जा रही है. बेसिकली इट इज नॉट इंटरफेरेंस, बट सो इंटरफेरेंस में कैसा होता है कि लाइट की इंटेंसिटी जो है वो सेम रहती है, ब्राइट डार्क, और उसकी विड्थ भी जो है वो भी सेम रहती है. बट यहाँ पे ऐसा नहीं हो रहा है. बट अगेन जो न्यूटन्स रिंग है उसमें बेसिकली तो इंटरफेरेंस ही हो रहा है. वी आर गेटिंग सच काइंड ऑफ पैटर्न. सो ऐसा क्यों हो रहा है वो थोड़ा हम समझते हैं. सो यहाँ पे जो है वो कुछ एयर फिल्म का ये जो डिस्टेंस है वो जैसे जैसे यहाँ पे डिस्टेंस बढ़ता जा रहा है, वैसे वैसे ये जो डिस्टेंस है वो भी बढ़ता जा रहा है. उस हिसाब से यहाँ पे जो है वो इंटेंसिटी कम होती जा रही है. और ये जो डिस्टेंस जो है वो भी वेरी कर रहा है विथ रिस्पेक्ट टू सेंटर टू द सम डिस्टेंस, एंड दिस बिकॉज ऑफ एयर फिल्म. So this is the main logic behind that. Basically, it is purely because of interference pattern. Yeah. So there is some realistic image, or you can say that instrumental image of the Newton's ring. There is a traveling microscope. Then we will get some interference Newton's ring through the interference. Yeah. Again, concept is very useful. But in the case of Newton's ring, whatever interference is occurred, it is due to reflected light, because here a reflected light is superposed to each other and interference. So in that case, the middle, or you can say that the center is a dark, and when center is bright, then we can say that it is not from the reflected light. It is an interference due to a transmitted light, and then it's happened कि यहाँ सेंटर जो है वो कुछ ब्राइट हो सकता है और रिफ्लेक्टेड लाइट में यहाँ पे डार्क होता है. यस. सो न्यूटन्स रिंग बेसिकली रिफ्लेक्टेड लाइट की वजह से जो है वो कुछ इंटरफेरेंस मिलता है, तो हमें ऑलवेज बीच में जो है वो कुछ डार्क ही मिलेगा. ओके. So let's focus on the Newton's particle theory. So first न्यूटन्स जो है उन्होंने ऐसा बताया था कुछ 17वीं सदी में कि लाइट का नेचर जो है वो पार्टिकल है, and which is he described in his optics. There is a book. Okay. So उन्होंने जो लिखी थी और उसमें से ये कुछ जस्ट थियरी दी थी, कुछ एक्सपेरिमेंटल कुछ पर्पस वगैरह या फिर कुछ एक्सपेरिमेंट नहीं किया था, और ऐसा ही बता दिया था कि लाइट जो है वो पार्टिकल से बना है या फिर वो पार्टिकल नेचर है. देन आफ्टर हाइजेंसाई एंड 1801 में उन्होंने वेव थियरी जो है वो दी, और कुछ वेव थियरी जो है वो कुछ इट इज अ फंडामेंटल कॉन्सेप्ट इन द स्टडी ऑफ वेव प्रोपगेशन, एंड ये कुछ उन्होंने डिस्क्राइब किया था ट्राइटे डेला ल्यूमिरे, एंड दिस इज अ बुक जो उन्होंने लिखी थी, और उन्होंने इसमें कुछ वेव थियरी का जो है वो कुछ वर्णन किया था. तो इनके अनुसार जो है वो लाइट जो है वो वेव के फॉर्म में ये जो है वो आती है. देन आफ्टर थॉमस यंग कम, एंड उन्होंने जो है वो डबल स्लिट एक्सपेरिमेंट किया. सो इट इज अगेन वेरी इंपॉर्टेंट. डबल स्लिट एक्सपेरिमेंट किया कि लाइट को जो है वो कुछ एक स्लिट में से निकाला, और फिर उन्होंने 2 स्लिट लेकर S1 S2 लेकर यहाँ से कुछ जो है वो लाइट आगे बढ़ाई, एंड दिस इज एक्चुअल इमेज ऑफ द लाइट, एंड वी विल गेट सम इंटरफेरेंस पैटर्न लुकिंग दिस. सो experimentally prove that he experimentally proved that light is a wave. Then after Einstein comes and gave a photoelectric effect, whatever light is coming and incident on the metal surface, then atom is absorbing the energy and release some electron, and that is called a photoelectron. So यहाँ पे हमको पता चला कि एक्सपेरिमेंटली जो है वो लाइट जो है वो पार्टिकल है। अब कंफ्यूजन बहुत है कि लाइट पार्टिकल है या वेव है, उसके बारे में थोड़ा हम डिटेल में आगे जाएंगे। तो कुछ डबल स्लिट एक्सपेरिमेंट तो हो गया था, लेकिन कुछ मॉडर्न तरीके से हमने डबल स्लिट एक्सपेरिमेंट परफॉर्म किया, और उसमें लाइट ना लेते हुए इलेक्ट्रॉन गन लिया, और यू कैन सी दैट फ्रॉम द इमेज। इलेक्ट्रॉन गन से हमने इलेक्ट्रॉन को जो है वो डबल स्लिट में से जो है वो निकाला, और उसके सामने जो स्क्रीन थी, मान लो कि कुछ 2-3 हजार इलेक्ट्रॉन जो है वो हमने डबल स्लिट में से निकाला, और उनके सामने जो स्क्रीन थी वो हमें कुछ इस तरह से पैटर्न दिया, एंड इट्स पैटर्न इज अ वेरी लुक लाइक इंटरफेरेंस पैटर्न। सो ये अगेन हमें सोचने पर मजबूर कर देता है कि इलेक्ट्रॉन जो है वो वेव बिहेव कर रहा है या ये खुद पार्टिकल है। सो अगेन ये कुछ क्या हो रहा था क्या नहीं हमें कुछ पता नहीं था, तो उस हिसाब से हमने यहाँ पर जो है हमने यहाँ पे तो कुछ डिटेक्टर नहीं यूज किया, लेकिन हमने यहाँ पे कुछ डिटेक्टर रख दिया। अब जैसे ही हमने डिटेक्टर रख दिया, सो इलेक्ट्रॉन जो है वो अपना वेव नेचर भूल कर अब अपने खुद के पार्टिकल नेचर में वो वापस आ गया। वी आर कोलैप्सिंग द वेव राइट हियर, and whatever we are observing that path of the electron, then suddenly electron change its behavior from the wave to the particle. So again question arise why it's happened कि एक्चुअल में इलेक्ट्रॉन जो है वो पार्टिकल है या वेव है। सो कुछ इस तरह से हमें पता चल रहा है, जो हमारा ये कॉन्सेप्ट है वो जब हम नहीं देख रहे होते तब इलेक्ट्रॉन जो है वो कुछ अपना वेव नेचर बताता है, और जब हम उसको ऑब्जर्व कर रहे हैं तब ये जो है वो अपना पार्टिकल नेचर बता रहा है। बिकॉज पार्टिकल जो है वो यहाँ से, यानी इलेक्ट्रॉन जो है वो यहाँ से जाएगा इंडिविजुअली, तो सीधी बात है यहाँ पे जो अगर गैप है तो यहाँ पे ही वो इंसिडेंट होगा या फिर फॉल होगा। तो यहाँ पे बहुत ही डिफरेंट, और यू कैन से दैट इट्स अ काइंड ऑफ मैजिक थिंग। जब हम उनको देख रहे हैं तब ये जो है वो पार्टिकल नेचर शो कर रहा है, और जब उनको नहीं देख रहे तब जो है वो वेव नेचर शो कर रहा है। इट इज अ वेरी सिमिलर लाइक दैट। जब हम बाहर निकलते हैं और हम लोगों के नजर में आते हैं तब हमारा बिहेवियर जो है वो वेरी डिफरेंट होता है। एंड जब हम अकेले होते हैं, जब हम घर में होते हैं, तो हमारा नेचर जो है वो कुछ अलग ही टाइप का होता है। तो ये
सर इसका क्या मतलब है कि जब कोई उन्हें देख रहा है?
या एग्जैक्टली अगर देख रहा है यानी इट मींस दैट डिटेक्टर हमने बीच में लगाया हुआ है ना। यहाँ पे हमने देखा कि जैसे हमने बीच में डिटेक्टर लगाया हुआ है, ठीक है, तब जो है वो कुछ पार्टिकल नेचर शो करता है। अब ये क्यों हो रहा है, कैसे हो रहा है, वो हम थोड़ी ही देर में आगे देखेंगे कि उसका एग्जैक्टली कॉन्सेप्ट क्या है, कि ऐसा रीजन क्या है कि क्या हो रहा है। So this means of the wave particle duality. Then after, so Richard Feynman say that if you think you understand the quantum mechanics, you don't understand the quantum mechanics. And again, basically quantum mechanics, if I tell you what happened, it won't happen. So so it is a very interesting thing. कि हम जब इलेक्ट्रॉन को देख रहे हैं तब ये पार्टिकल नेचर शो कर रहा है, और जब नहीं देख रहे हैं तब ये जाकर जो है वो वेव नेचर शो कर रहा है। बेसिकली इट्स सो दिस conclusion over here, the wave like nature of this probability amplitude allows for interference effect to occur, leading to observe wave like behavior in experiment. And however, when a particle are measured or detected, their wave function collapse. जब हम उनको देखते हैं तब जो उसका वेव फंक्शन जो है वो कोलैप्स हो जाता है और कोलैप्स टू द स्पेसिफिक स्टेट, वो कुछ स्टेट में आके रुक जाते हैं जब हम उसको मेजर करते हैं या फिर डिटेक्ट करते हैं तब। एंड तब जो है वो हमको कुछ पार्टिकल बिहेवियर जो है वो दिखता है। एंड दिस इज द मेन कॉन्सेप्ट बिहाइंड this dual nature. And again, light is so there is a conclusion over here. Light is a wave or particle. I think it's both, and it's depend on the condition and observation and a different situation कि light जो है वो कहाँ wave है कहाँ particle है। तो basically it's a wave and again it's a particle. It's a particle. Yeah.
Sir, can I do a very small comment with that? Concluding results with electron, you can't really conclude them with light because they do have quite inherently different phenomenon for the dual nature. So concluding that electron, yeah.
Also, sir, you
So-
can proceed.
Yes. So this is my contact number and email ID. So thank you for your attention, and yeah, I conclude over here. Yeah, thank you. Yeah, please ask a question.
Thank you, Kaushal sir, for such a nice talk. I find it very interesting when you show so much animation and you presented a difficult topic into a very easy manner. I hope many students have learned so much thing from this presentation. And now this session is open for questions. You can ask questions. Please, participants, if you have questions, unmute yourself.
I think there is some question in the chat box. Kaushal sir, please look on that
Yes,
question.
yes. We may say when the particles are generating from the source, showing the particle nature, and when they are traveling through a space or any medium, are showing a wave nature. You can say that like that, but again, the concept is again is that collapsing that wave function, and they convert to the specific state, and that is showing a particle nature.
Yes, but like we have electrons and associated wave functions, and then with it, when you put a detector for the position, then they collapse to the position space wave functions, and then you say, okay, my wave function is collapsed. Then, you can detect very precisely the position of electron, and so the momentum uncertainty is really approximate to infinity, and so electrons will really show the particle nature because we can see this precise position, and they will be no longer act like a wave because momentum uncertainty is really infinity. But can I do a small comment here?
Yeah, sure.
Okay. So
You can
so
also
by-
write something.
because there's no other question, then I want to make a very small comment, because sometimes I teach and this comment each time I do tell to my students something like, okay, when electron position is very precise, mean the wave function collapses to the position space wave function as written on one of the slides. Okay, but the wave functions for a very precise momentum will be written like exponential ikx. Okay, and if wave function is exponential ikx, then you see it is a sinusoidal wave in the space, and it is a periodic wave. So the position uncertainty in the space is infinite. When you add two exponential ik1x plus exponential ik2x, you will get so you will get this wave packet. And if you add, if you start summing much and much exponential ik1x plus exponential ik2x for the infinite number of k's, so at the end you will get a very, very narrow wave packet. That, and if you sum from k equal negative infinity to positive infinity, you will get a precise delta function. So in delta function, and delta function pointed at x0. So in this situation, you have this position uncertainty, which is very, very nil, approximately 0, and the momentum uncertainty, because you have added from k0, from k equal negative infinity to k equal positive infinity, so you have infinite momentum uncertainty. And as we have seen, that this diffraction or interference phenomenon is a result of this wave nature, and we are if there are wave of infinite wave numbers, so we really won't observe any interference pattern. So that's one of the quantum mechanical explanations why electrons show this
nature. Yes. Particle law.
but
Yes.
yes, but
Very nice.
but there is a book by I don't know who written this book. Maybe somebody written a book, Cosmos. It is kind of scientific novel, but they've written an explanation that electrons are traveling through space, and
Yeah.
there is associated probability waves are also traveling, and at the and at the end, electrons go through the slits, and their associated probability waves, they interfere. And if associated waves interfere, we see a interference pattern over there. But there are in-call messages then.
Kaushal sir, there is another question
Yeah.
in chat
Yes.
box.
So from the Mr. Balaji, sir, can you please explain what is really happening when two waves can cancel each other to produce a dark spot? Because I can understand what is happening from the wave diagram, but when we describe or imaging it like a wave of water, what really cancel out the positive and negative peaks? Is there is any opposite force acting between the two opposite peaks to bring them flat? Yes, exactly. Just a minute, I present my screen again. Yeah. Okay. Can you see my screen?
Yes, sir, we can see your
Okay.
screen.
Okay. So in constructive interference, again, I told you, whenever phase is same, whenever phase is same, okay, then our amplitude is double, because of some mathematical equation over there. I have already told. And whenever phase is out, so there is in constructive interference there is some in phase condition. In phase is meant it means that there are both are in same phase, okay. And in destructive interference there are in opposite phase, or you can say that out of phase condition. The so phase is 180 degree, and they cancel out each amplitude. So here is a minus, sorry, here is a +1. हम मान लेते हैं अगर कि यहाँ पे अगर +1 है तो यहाँ पर जो है वो -1 है, एंड अगर जब हम दोनों को ऐड करेंगे तो जो होगा वो 0 होगा. देन वी कैन सी दैट सम देयर इज नो एम्पलीट्यूड ओवर हियर. एंड सीधी सी बात है, अगर इंटेंसिटी की बात करें, अगर लाइट इंटेंसिटी की बात करें, तो वहां पे लाइट इंटेंसिटी इट्स डायरेक्टली प्रोपोर्शनल टू ए एम्पलीट्यूड स्क्वायर, ए स्क्वायर. बट हियर एम्पलीट्यूड इज 0, then intensity is 0. So there are some dark spot because of that destructive interference and because of out of phase condition. Yeah.
There is one question more from Dhayasa. He is asking that both the reflected rays are parallel, then how would they interfere?
Sorry, I just.
He asked question very much earlier.
Okay, 1 second.
At 3:33 p.m. he asked this
At
question.
3:33 p.m. Okay, 1 second, 1 second. Yes, but both the reflected rays are parallel, and how would they interfere? They interfere. Yes, exactly. I think that ये कुछ question कहीं से भी आ सकता है. Yes. 1 second. Again, I.
So I think he's asking from one of your presentation, and it is very interesting question.
Yeah, it's a very interesting question, and it's very much aware of this my presentation. Yeah. I'm very happy to see that. Yeah. यहाँ पे ये जो BE and DF जो है वो both are parallel reflected rays, and मैंने बोला था कि ये जो आगे जाके कुछ superpose करेंगे, but here we are only focusing on for the one ray. Okay, so there are lots of ray incident on this plano-convex lens and reflected lots of रेज. ओके, तो कुछ यहाँ पे एक रे की बात नहीं है, जब यहाँ पे बहुत सारे रेज जो है वो आएंगे और कुछ आगे जाके इंटरफेरेंस होंगे. सो दिस आंसर फॉर दिस your question.
Yes, but okay, this guy might get a comment who is asking. There is a concept that not for the exactly for the interference, but for the diffraction, and what happening here is a class of diffraction as well. So there is a Fraunhofer diffraction, and it happens when two rays are parallel, and exactly they meet at infinity. But what happens? We are putting a traveling microscope, and the both lenses in the microscope, they act like a telescope, and we are exactly seeing what is happening on the infinity. So this is actually a Fraunhofer kind of interference or diffraction. It is class of diffraction, but there is absolutely no difference between the interference and diffraction. So we are getting here Fraunhofer class of interactions.
Sir, there are a few questions more in the chat box. Kaushal sir, can you read them or should I read it for you?
Yeah. Yes, I can read a simple out. The pattern obtained in modern double slit experiment as a shown diffraction pattern. Easy. Again, I'm telling there is no difference between interference and diffraction pattern. Okay, so in the interference, so whenever diffraction occur, so in that diffraction there is always interference is in that portion. So that is yeah, exactly. You can say that it's a diffraction pattern. Yes. Basically, no difference between these two. Yeah. Then, sir, how can we clearly explain that why electron particle behave as a wave in double slit making interference pattern? मैंने इसका आंसर जो है वो टॉक में दे ही दिया है बेसिकली कि इस तरह से क्यों जो है वो इलेक्ट्रॉन अपना नेचर जो है वो एज अ वेव के फॉर्म में बता रहा है. And already Mr. Tripathi is also told. Yeah. So is there any difference between sound wave interference and the light wave interference? Basically, there is no difference. Just so light wave, it means what you understand. What is the meaning of light exactly? So yes, Lavanya. Yes, tell me what is the light, or what is the light wave? It's a very interesting question. Lavanya, Rajesh.
We might have problems with the microphone.
Lavanya, can you please speak again?
It is better to write in chat box because your microphone is not very efficient, at least here in discussion.
Yeah. So basically, we call a light is a visible region of the radiation. Okay, so there are various regions, uh, visible region and IR and UV and X-ray and all this. So among them, so light wave is basically the visible region. Okay, and sound wave is also a different wavelength. So here, difference between the sound wave interference and light wave interference is only just wavelength, uh, it's no difference between phenomena and kind of this. Yeah.
Well,
I
I just
think
want to
I
make
would like to comment here. So I think there is a basic difference between light and sound wave. So sound wave is a mechanical wave.
Yeah.
And light is electromagnetic wave. So there is a basic difference. And yeah, that's it.
yes, and there is a very huge difference when we do a theoretical framework. So electrons are non-relativistic particles, and we can straightforward do quantum mechanics for them. Again, sound wave as phonons, they are not particles, and we really can't do a straightforward quantum mechanics, but we need a two-component quantum field theory spinor framework for the phonons.
I think can I comment here? So it
Yeah.
depends upon our treatment. How do we treat? Like Dirac equation. So their electron has been treated as a relativistic case, not non-relativistic. Okay,
Yes.
so it depends on treatment. So that is another topic of discussion. So let's not bring that here. Okay, so that would be better. Yeah, so that we can discuss sometime. Okay, so like Dirac equation, they have developed Dirac equation. That is relativistic phenomena, right? And Schrodinger equation simply non-relativistic phenomena, right? So both things are different. So like people have used relativistic mechanics to explain the conductivity in graphene sheet using Dirac equation, field theory equation. So that is being done now.
Yeah.
Yeah. So
Somebody is asking difference between diffraction and interference.
yeah. So it's a very basic difference. So whatever light is incident and they go through some slit kind of thing, or some edge of that slit, then they deviate that path and will get some diffraction pattern. And also again, I told you that equation, or you can say that condition over there, lambda is greater than or equal to d, and we will get some diffraction. Basically, there are no difference between interference and diffraction. But again, when we find out in a very quantum level, or you can say that a very small micro level, we can find out some difference between the interference and diffraction. So in interference, there are the again, width of that particular fringes is same, dark bright, dark bright, dark bright, and all this. And also intensity of that dark bright is all are same. But in diffraction, there is some width of fringes are not equal, and again, intensity of all the fringes are not equal. So this is basically the main difference between the diffraction and interference. Yeah.
Sir, I would like to
Please.
add a point here. Like interference, the basic definitions of these two terms, wherever we used it. In interference, there should be at least two waves, and for diffraction, that means deviating from its original path. For diffraction, the wavelength of the light should be same as the size of the particle. That should be the main condition.
Yeah.
Can I also make a small comment? There is a very nice comment by Ankit that the main difference between only at macroscopic level, because it has nothing to do with microscopic, the main difference is the interference, is the interaction of two wavelets, while the diffraction is the interference of secondary wavelets. They are originated by the same wavefront. So in interference, two wavefronts are required, while in diffraction, secondary wavelets originated from the same wavefront, the diffract, like they interact, and you will see. But there is at any level I really won't be able to differentiate that this is a secondary wavelet or this is the main wavefront at any level. So at the microscopic level or at the quantum level, they are just summing of two intensities. You can't say it is an interference or it is diffraction. So at the end, like you will use a different word. It is called intensity modulation, but intensity modulation or intensity sum. But yes, Ankit has given a very, very nice point that for diffraction, one wave is sufficient. For interference, we need two. Yeah.
There are two waves.
Yeah.
Two or more, there are two waves and superpose, and again, intensity is higher, lower, or same. Yeah.
I think there are no more doubts. We can conclude this session now. Captain sir, shall we?
Before that, we should take a photograph of the session. So please request everyone to switch on their camera so we can take the photo. So then you can.
That one is the hardest session for me.
Ankit sir, please take the snapshot. You do it better.
So you can take a screenshot.
I think Ankit would have taken the screenshot.
Sorry?
Ankit, have you taken the screenshots?
No, sir, I have not taken the screenshot. I'm waiting for all the participants.
Okay. Yeah, so please take the screenshot.
I've taken it.
Okay, now you can continue.
Okay. So now we can leave.
Ankit, I think. Hello. Ankit, are you there?
Yes, I am here.
Yes, so please conclude the session now.
Okay. So there was a talk and a very interesting talk, and after that we have very much discussion on basic optics and interference. And I would like to thank the speaker to spare the time and giving the talk. And I would also like to thank Tripathi sir for valuable raising the points. And thank you all the participants for joining. And if more queries, you can post your question in the Google form. And here I am ending the session.
Thank you, sir. Thank you.
You can leave yourself.
Bye-bye.
Thanks to all.
Yeah. Thank you so much for the attention. Yeah.
Kaushal sir, thank you, Dr. Captain. Thank you, Ankit
Yes, sir.
sir.
Thank you, sir. Thank you so much.
Thank you, sir.
Sanjay sir, can we do meeting here? Captain sir, if you can stay.
Yeah, no problem. I can.
After we can reconnect, I think.
Yes, at anytime, sir.
Yeah. Yeah.
Whenever you
10 minutes after 10 minutes?
yes,
You're fine, Sunil sir?
No,
yes,
just
for me it's
1 or
fine.
2 minutes. We can just switch off the recording and
Okay.
Yes.